Okay, so here we're going to work on an example where we solve an initial value problem using Laplace transforms with a piecewise function. So we have y double prime plus y being equal to this piecewise function here, and here's some other key information involving step functions and the Laplace of step functions, as well as finding the Laplace of derivatives, because those will be useful when we work on this. So let's get started. First, we will need to rewrite this differential equation without the piecewise function. So we'll be multiplying each piece of the function by a stepwise to mimic the interval from 0 to 4 and t greater than 4. So we're starting with 3. We'll have 3 times u sub 0, which is just 1, but I like to write it anyway. U sub minus u sub 4 of t plus the next one, 2t minus 5 times u sub 4 of t. So just to go over again why we do this is we want to essentially mimic these functions with these intervals. The step function where a is 0, to the left of a is going to be 0, to the right is 1. We are only going to the right of 0, so this is going to be 1. That's why I said this is just going to be 1. Minus u sub 4, or u sub 4 of t, the step function of that. To the left of 4, it's going to be 0, so you're going to have 1 minus 0. And then after 4, it'll be 1. So these essentially will only hold on this interval from 0 to 4 with that value of 3. Similarly, greater than 4, we know, again, we're just looking at 1. It's going to be times 2t minus 5, so that will take care of that interval. Now we have to do some manipulation potentially. So we will distribute some terms. 3 times u sub 0 of t minus 3 of t plus 2t times u sub 4 of t minus 5 u sub 4 of t. So we distributed terms. We look like we have a like term here. Might as well clean that up a little bit. Y double prime plus y being equal to 3 u sub 0 t. Right, the plus 2t times u sub 4 of t first, and then that will be minus 8 times u sub 4 of t. So now that we have that, we want to rewrite in a form that will help us use these Laplace transforms of the step functions to find them and help us solve. As of now, not all of them are good. This one, 3 times u sub 0 of t, that's fine because just 1, and we can find the Laplace transform of that fairly straightforward. Similarly, well, not similarly, but this one is where we need to adjust something. Minus 8 u sub 4 of t. That again is also okay because we don't have to adjust it at all. It's just, this is just 1 essentially, and we don't need to worry about that. But we can adjust this term here a little little bit, and we have to, so I'm going to do that. 3 times u sub 0 t plus 2 times t plus 4. Whoops. I want to write this as t minus 4 plus 4 times u sub 4 of t minus 8 times u sub 4 of t. And by doing that, by the way, now I create, if I just look at this part, t minus 4, u sub 4 of t with the step function where 4 is a, that will fit this form right here. So we will be able to find the Laplace of that. I just need to manipulate it some more, or simplify some more. So let's do that. 2t minus 4 times u sub 4 of t plus 8 u sub 4 of t minus 8 u sub 4 of t. So, just because it's easy to miss, this term 8 u sub 4 of t comes from when you have to, when I split this apart, 2 times t minus 4 times u sub 4 of t, 2 times 4 is 8 times u sub 4 of t, and that's where that comes from. So, nice thing is this cancels out, and we are left with these terms here. Y double prime plus y equal to 3. Step function where a is 0 plus 2 times 2 minus 4. Step function where a is 4. And that is it. So now we can actually take the Laplace of each of those to help us out. And then that is where we will look at this stuff to kind of help us along to continue this problem. But let's write it in the Laplace transform notation. So the Laplace of y double prime plus the Laplace of y being equal to 3 times the Laplace of u sub 0 t, which, by the way, again, u sub 0 t is just 1. I just like to write it because it reiterates it for me. Plus 2 times the Laplace. And I'm going to write it in this form just because it really mimics what's above in the corner, so I can use that. T minus 4. And yeah. So, writing it in the Laplace transform notation there, we now can use this bottom information here to help us write out the upper terms, which is going to be s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0 plus the Laplace transform of y. And that is all equal to the stuff on the right, which I'm just going to do the Laplace of the step function. Again, it's just 1, so we know that that fits this form of just 3 over s plus 2 times, then we have the Laplace transform of this stuff, which again we know that's going to be e to the negative as, and a is 4 in our case. So it's going to be 2 e to the negative 4s over s squared. And that comes from, again, if you need a reminder, I wrote some other stuff down here. Laplace transform of t to a power is just n factorial over s to the n plus 1. And in the case up here, this just represents a t to a power, and that power is 1. So when you add 1, you got that. And of course, 1 factorial is 1. So now what do? Now we got to simplify, right? So let us simplify a little bit more. I should at least point out above the initial conditions here. Yeah, the initial values. Y of 0 was 1. Y prime of 0 is 0. I'm going to plug those in for here. Maybe I'll just highlight it here so I don't lose my place. Alright. Going down, we have, and I'm going to rearrange things just to try to save some space here. S squared Laplace of y plus the Laplace of y minus s, and then 0, which I won't write, being equal to 3 over s plus 2 e to the negative 4s over s squared. And then, now what do? Get the Laplace transform of y by itself, factor it out, and get s squared plus 1 times the Laplace of y being equal to 3 over s plus 2 e to the negative 4s over s squared plus that s term. And when we get the Laplace by itself, we got to divide by the s squared plus 1. So doing that, we will have the Laplace of y is equal to 3 over s times s squared plus 1 plus 2 e to the negative 4s over s squared times s squared plus 1 plus, simplifying this, you're just going to have, not simplifying, sorry, s over s squared plus 1. Whew. This is taking a long time. All right. So now we need to get y of t, because our whole goal is to find what y of t is, and if we remember, we know that, let's do this first. We know that the Laplace transform of function y, we usually call that equal to some big y of s. And what's nice about that is if we take the inverse Laplace of that big y of s, that is just equal to the function y of t. So that's what we do. We will take the inverse Laplace of everything. So we know, I'm going to rewrite it like this, y of s equals, and I'm actually going to split this up because we have to. We know we're going to have to do some kind of partial fraction decomposition with these two. This one's okay. The Laplace, or the inverse Laplace transform of that is something nice, and I'll actually scroll up a little bit now so we can see that. If you remember, that's just cosine, so that's nice. But we do have to break down these other terms, and we got to use partial fractions, which I'm not going to do because I'll leave that for you, just for the sake of time. So the partial fraction decomposition for this is just going to be rewritten as 1 over s minus s over s squared plus 1 and then we will have plus 2 times e to the negative 4s, and breaking this down, if again using partial fraction decomposition, you would end up with 1 over s squared minus 1 over s squared plus 1. And then we have plus s over s squared plus 1. So, what we can do now is I'll just rewrite this all out. So then I can take the inverse Laplace of each of them by themselves. I'm going to write them so it's fairly straightforward to see. 2 times e to the negative 4s squared plus 2 times e to the negative 4s squared plus 1. Almost made a mistake. Plus s over s squared plus 1. Okay. All right. After all of that, now I can take the inverse Laplace of that big ys, and that will give us y of t, which is awesome. And that is just, I'm going to rewrite it, 3 times the inverse Laplace of 1 over s minus 3 times the inverse Laplace of s over s squared plus 1 plus 2 times the inverse Laplace of this e to the negative 4s over s squared minus 2 times the inverse Laplace e to the negative 4s over s squared plus 1 plus inverse Laplace of s over s squared plus 1. Okay, so almost done, I promise. We actually really are. So I'm going to scroll down here a little bit. Y of t, we have it. We just need to clean this up. The inverse Laplace of 1 over s is just t to the 0, which is 1. So we have 3 times 1, I guess. I'll write that. Minus 3 times the inverse Laplace of s over s squared plus 1. You can see up here, that's just cosine, with a being 1. So it's just cosine of t. Plus, and then this is where we do have to kind of remember the reverse of what's up here. We do have to remember our step function stuff, and we have to take that into account. So doing that, let me write the 2 at least. The inverse Laplace of e to the negative 4s, that means we have our step function where a is 4 times, and then the Laplace of inverse Laplace of 1 over s squared is just t, but remember we do have to keep this in mind, that the step function, it starts at 4, so we need to take that into account and write times t minus 4. And then similarly, minus 2 times, and then e to the negative 4 tells us there is a step function there, and this 1 over s squared plus 1 is related to the Laplace of sine, so we know that that's going to be sine of t minus 4, because again, a is 4, and plus the Laplace, the inverse Laplace of s over s squared plus 1, which we already found and conveniently works out to be right under the other cosine. So we see we can simplify, and that is the last and final step I'm going to do here, so yay! Negative 3 cosine t plus cosine t is just negative 2 cosine of t plus, and for cleaning up's sake, I will factor out a 2 use of 4 from each, so it just kind of looks a little nicer. You don't have to do that, but I will. U sub 4 of t, and then over times, and then there's this t minus 4 minus sine of t minus 4. And one last thing, just to keep you on this video, I guess. Box in the answer. There we go. And that is our function that fits this initial value problem. So I hope that was helpful.